Hello, this video covers section 11.6 from your textbook. It's all about inverse functions, and by the end of the section we will work up to being able to actually find an inverse function if we are given a function. And the very first thing we're going to start with is a review item, and that's using the vertical line test to determine whether a graph is actually a function, because we can't find an inverse function if the original is not a function itself. So take for instance this first graph. If we were to put a vertical line, I'm just going to put one for example here in red. Vertical line. This particular vertical line only crosses the graph at that one place right here, and no matter where you put any vertical lines, each vertical line will only pass through the graph in one place. And if that's the case, then we have what is called a function. So this particular graph, graph 1, is a function. But I hope you can see that the second graph is not a function, because if I pass a vertical line through this graph, we can see that this vertical line crosses in two places, right down here and also right here, which makes graph 2 not a function. So first of all, we need to be able to tell when we actually have a function. Now, once we have a function, then we can start to talk about whether or not a function is one-to-one. A function being one-to-one is one of the requirements we're going to see that is necessary for an inverse function to exist. And let's read here. It says, for a function to be one-to-one, it must be a function, i.e. it must pass the vertical line test. We already said that. And each output must be associated with only one input. Okay, so we have a couple of examples here. We're going to show an example of something that is one-to-one and show us an example of something that's not one-to-one. So if I were to take an example that is one-to-one, that means each output is associated to only one input. So maybe this output A is associated with 6, and maybe output 7 is associated with an input of maybe output C is associated with an input 7, and maybe output B is associated with an input of 5. So these would be our inputs, and these would be our outputs. Now, if I wanted to give you an example of something that's not one-to-one, that would mean that we had an output that was associated with more than one input. So maybe we had D, maybe D was associated with 1, but also with 2. And then F was only associated with 3. The problem here is this part right here. Here we have an output of D associated with 2 different inputs. And we'll see why that's a problem here in a little bit, but as far as a function being one-to-one, that can't be the case. So this is an example of a function that is not one-to-one. We could also take a look at sets of ordered pairs and see which is one-to-one and which is not one-to-one. Notice here we have output of 5 associated with -2. 2 is associated with -1. -1 is associated with 0, and -4 is associated with 1. There's no case where we have an output that results from 2 different inputs, but in option 2, if we look at this ordered pair and this ordered pair, they both have outputs of -7. So we have -7 coming from an input of 0 and from -2. So in this example, this would be an example of a function that is not one-to-one. And there is a shorthand for writing one-to-one. Instead of writing it this way, we can also write it as 1-1 for one-to-one. Now the first one we said that this function is one-to-one. but the second one is not 1 to 1. And we can use the horizontal line test to determine whether a function is 1 to 1. Horizontal line test says that if a horizontal line passes through a graph at more than one point, it means that there are two values that are associated with only one y value. So the function is not 1 to 1. And so now we can go back to our two graphs at the beginning to see which of the graphs represents a 1 to 1 function. Well, graph 1, remember we said is a function, but is it 1 to 1? Let me use a different color here. If we pass a horizontal line through, it does not cross in only one place. It crosses in two places. So this means that this is not 1 to 1. In graph 2, we don't really care about graph 2 because it wasn't a function to begin with, so we don't care if it's 1 to 1. But unless we were to take and only talk about the top portion of this graph. So maybe we only talked about that, and let's say that this bottom portion of the graph was deleted. If that was the case, and we were just looking at the top, in other words, let me put a little window around here. If we were just looking at this portion of it, the graph, and we passed a horizontal line through there, we can see that in that portion of the graph, the graph would only cross the horizontal line once, which would make it 1 to 1, but only if we restrict a graph to being just the top of it. So let's go back here. Now let's talk a little bit more about this idea of inverse. We already know several functions that are inverse functions. Just from when you're introduced to solving equations, we know that adding is undone by subtracting. And we know that multiplication is undone by division. Those are opposite or inverse operations. The word I like to use here for inverse is the inverse functions undo each other. Whatever a function does, its inverse function undoes that. So another type of function that we've looked at already is the square root function. Let's say, what if we call function f the square root of x? How do we undo a square root? Well, we should know that it gets undone by squaring it, right? X squared undoes the square root of x. Well, let's see how this works. Let's say, for example, we have an input of, let's say, 16. Well, if we take that 16 and we put it into our f function, what does f do? F takes the square root of it. So f would turn that 16 into a 4. Well, if we then take that 4 and we run it through g, remember f was the square root, and g is squaring it. If we square 4, it spits back out 16. So can you see that the input and output values would be swapped for inverse functions? Look at this. For f of x, the input is 16, the output is 4. So, it kind of looks like this. If we have x and square root of x, if the input is 16, the output is 4. Or if the input is 9, the output is 3. Whereas for g of x, if we had x and x squared, then 4 would turn into 16, and an input of 3 would turn into 9. See how they're swapped? 16, 4, or 4, 16, 9, 3, 3, 9. These are inverse functions because they undo each other, but also we see that that causes their inputs and outputs to be swapped, turned around, which is really nice for when we want to try to graph an inverse function later on. So how can we tell whether two functions are inverse functions? It turns out that if you remember what we did last section where we were talking about taking the composition of two functions, if you compose a function with its inverse, you get your input back. And this should make sense just from the picture we talked about. If we first take our input and put it into the inside function f, and then we put it into the outside function g, we get back what we started with. In other words, what I'm saying is if we take x and we put it into some function g, and that spits out g of x, or actually let's use this notation. If we put it into f, and that spits out f of x, then if we put that into our inverse function, which we haven't written this notation out yet, but the inverse notation is f with this little power of -1, then that gives us back x. And we'll talk about this notation in a little bit, but so this is the result that we just found. We said if two one-to-one functions, f of x and g of x, are inverse functions, if f of g of x equals x and if g of f of x equals x. So we can use this to determine if these two functions are inverse functions. First of all, f of g of x, we want to calculate that. So if we put g inside of f, remember f looks like 3 times something plus 4. And what are we putting into f, the 3 times something plus 4? We're putting in g. We're putting in x minus 4 over 3. Well, what's happens when we try to simplify this, if we treat this like 3 over 1, then the 3's cancel, and we're left with x minus 4 plus 4, which is just x. Notice this was what we said should happen if they are inverse functions. We said that right here, f of g of x should equal x. And it should also work the other way around. We should be able to take g of f of x and also get x. So g looks like something minus 4 over 3. Now what goes into the x here? What's our input? Our input is f, and f is 3x plus 4. Well, see if we put that in, the plus 4 and the minus 4 cancel, and we get 3x over 3, which again we see is x. So we can say yes, f of x and g of x are inverse functions. F of x and g of x are inverse functions. Alright, but if we have a function, how do we find its inverse? And that's the next part here. This is what we are building up towards. Okay, notation wise, I already mentioned this. If the notation for inverse function has this little -1 power or superscript, that's how we denote the inverse of f of x. We use this notation. Be careful though, it's not really an exponent. We're not thinking of it as raising to the -1 power. It's just the notation that we use. And it's really just a 5-step process, and all the steps are very simple. They're outlined here in this box. So let's follow these steps, these 5 steps for this first example. We know step 1 is to determine whether the function is 1-to-1, and probably the easiest way to do that is just look at a graph. We have our graph. We know that it has a y-intercept of 6, and the slope is 2 over 1, so we go up 2 over 1. This graph is going to look something like that. Any horizontal lines going across the screen left to right, will only cross this graph in one place. So we would say yes, this is 1 to 1. So we can go ahead and move on to step 2. Now, step 2, outlined in the box here. Step 2 says that we can replace f of x with y. So we know that's the same anyway, so we can say that instead of f of x, we can say y is equal to 2x plus 6. Then we can move on to step 3. Step 3 says replace or interchange the x and the y. So instead of having a y over here, we're going to replace it with an x, and then on the right hand side, instead of a 2x, we'll have a 2y plus 6. Which brings us to the next step, step 4. Step 4 says to solve the resulting equation for y, we need to get y by itself, which means we'll probably start here by moving that 6 over to the other side. That's going to give us x minus 6 equals 2y. And we still don't quite have y by itself, so we're going to need to divide both sides by 2. That causes the 2's to cancel, and we end up with y is equal to x minus 6 over 2. All that right there is step 4. We're almost done. Now remember, we don't use, when we're talking about functions or inverse functions, we don't use y. So now we need to go ahead and call this. This is our inverse function. We need to call it in step 5. We need to call it an inverse function. So instead of y equals, we're going to say this is our f inverse. Our notation. There's our notation for f inverse. So the inverse function is x minus 6 over 2. Some of you may also wish to write this as f inverse is equal to 1/2 x minus 3. That's because we have a 1 over 2, which makes 1/2, and we have a negative 6 over 2, which makes negative 3. So you can write it in that notation as well. Okay, take a look at one that's a little bit tougher. Now, the last one was a little bit easier to graph than this one, so we might want to put this in our graphing calculator to see if it's 1 to 1. That's our first step. So if we turn on our graphing calculator and we clear our function and we put in x, and here we need to put divided by and then put parentheses, 3x minus 2. We have to put parentheses around the denominator to make it both the 3x and the negative 2 be on the bottom. If we don't put parentheses on, our graph will not come out right. And then we can go ahead and graph it. And it's not really a very good graph here as far as what we see. I think we should change our window. Let's change our window from -5 to +5 and -5 to +5 and see if that looks a little bit better. So just kind of zoom in on this graph. Okay, so on first glance it looks like this might not pass the horizontal line test, but this is one place where graphing calculators have a problem with, there's a problem with technology in that they actually put in things that are not supposed to be on the graph. There should not be any line here, any vertical line that's connecting this bottom part of the graph to the top part. In other words, the actual graph, it should look something more like this. The There's no vertical line that connects these two, and so no horizontal line will cross this graph in more than one place. That graph, the line that's the horizontal or the vertical line that shows in there, that's actually what we call a vertical asymptote, which we will put on graphs a little bit later in this course, but we're not going to do that right now, and it has nothing to do with the actual curve as far as being part of the curve. It's a line that the curve approaches instead. And so this is one-to-one. Each horizontal line will only cross the graph in one place, makes it a one-to-one function. We can move on to step 2, replacing f of x with y. And so we have y equals x over 3x minus 2. And we can move on to step 3, switching the x's and the y's. And now becomes the hard part, because we need to be able to get y by itself. We need to solve for y. And probably the first thing we should do is get rid of our fractions so we can multiply both sides of the equation by the denominator. And that'll cause this denominator to disappear, and then on this side we're going to want to distribute. So it gives us 3x y minus 2x equals y. And we're trying to get y by itself, and right now we have the problem that both we have a y on the right hand side and a y on the left hand side. We need to get them both on the same side. So what I'm going to do is subtract this y over to the left hand side, and I'm going to also move this 2x over to that side. I'm going to subtract 2x from both sides, and so, or excuse me, add 2x to both sides, because that'll cause the x's to cancel. And so we're left then with 3xy minus y, and then the y's cancel here, so we're left with 2x. And we're almost done. The next step, and if you've never done this before, it's not entirely obvious, but we can go ahead and pull a y out here, leaving 3x minus 1 equals 2x. And that, if we rewrite it, so we have y times 3x minus 1 equals 2x. We can go ahead and now take our last step of dividing both sides by 3x minus 1 to get y by itself. And so we have y equals 2x over 3x minus 1, which means our inverse function, if we put that notation in, is equal to 2x over 3x minus 1. This is one of the harder of these type of problems. I want to show you kind of how you go about doing that. If you get y in two places, like we did in this one, you get all the y's on the same side, and then you factor out the y so you can divide by the rest of the stuff. And the last part of this section is how we graph inverse functions if we know the graph of the regular function. So here's a function of f of x, and we want to sketch a graph of f inverse of x. And we're going to take advantage of the fact that we saw earlier in this video where the inputs and the outputs get swapped for inverse functions. Remember, we had the square root function, which turned 16 into 4 and 9 into 3. And we found that its inverse function turned the 4 back into 16 and the 3 into 9. That's the idea of inverse functions, because they undo each other. So we can use this idea to help us graph an inverse function if we have the graph of a function itself. For example, if the function turns an input of negative 3 into an output of negative 2, then the inverse function will turn negative 2 back into negative 3. It will also turn 0 back into negative 1. It will also turn 2 back into 1, and 4 back into 1.5. So what we can do is then put those points on the graph. -2, -3 is right there. Then we have 0, -1. Then we have 2, 1. And we have 4, 1.5. And so what this graph will look like if we were to continue this on and get a few more points, it's really going to look something kind of like this, which you can see this is a reflection across the dotted y equals x line. So if you look across this dotted line, it's at like 45 degrees. These two graphs are reflections of each other, and this is a result of inverse functions. In fact, anytime you have a function, its inverse function will always be a reflection of the original function across that dotted line. So that does it for that example. We can also use the same sort of idea, though, if we were just given an example of a one-to-one function that's given in ordered pair form. And remember, we have to check first that it is a one-to-one function, which we do see here. -4 has an input of 1, -1 has an input of 0, 2 has an input of -1, and 5 has an input of -2. So if this right here is the function, then we would say that the inverse function, f inverse of x, would be the set of ordered pairs that turns 5 into -2. It turns 2 back into -1. It turns -1 back into 0, and it turns -4 back into 1. See, all we did was we just switched the inputs and the outputs for the inverse function. And that does it for section 11.6. Thanks a lot. We'll see you in class.